All right, let's talk about substituents and how to name molecules that contain substituents within them. First things first, let's define the proper naming of such fragments. Technically speaking, substituents will only be things that stick out of the main parent chain in your organic molecule. So they'll be branching out of that main chain. And if it's all carbon, right, if you branched out section is just carbon, you use the same rule as before. You use the prefixes for carbon and you use the suffix YL. So methyl, ethyl, propyl, butyl, pentyl, hexyl, heptyl, octyl, nonyl, etc., etc. But if you do have other substituents, you do have to use the proper name for them. If you have one of the halogens, you would basically drop the IDE ending of the corresponding halide and you'll replace it with the letter O. So instead of fluoride, this is known as fluoro if it's bound to carbon. If it's chloride, you name it chloro. Then you have bromo for bromide and iodo for iodide. If you have an OR group bound to it, so technically an ether, you will name it as an alkoxy substituent. So let's say that this is a single carbon, so it's a CH3O that's bound to your parent chain. This will be known as methoxy. If it's two carbons, then this will be ethoxy, propoxy, etc., etc. If you do have a benzene ring attached to the main parent chain, we refer to the benzene ring as the phenyl group. And if the phenyl group itself is first attached to a CH2, which itself is attached to the parent chain, then this whole fragment is known as the benzyl group. Okay, in addition to that, there are other special molecules that do have common names that we're going to use in this class. And it has to do with the carbon chain that contains 4 carbons, butane. If you look at butane, there is another molecule that also has 4 carbons and a total of 10 hydrogens in its structure, and it is isobutane. Notice that all that really took place is that this CH3 was moved from the end carbon here to the middle. They both got the same formula, C4H10. This one, the most linear one, is called butane. The one that is branched is known as isobutane because it's the isomer of butane. All right, that's if you just have them as the parent molecules, but let's say that they actually branch out of a bigger organic molecule, in which case these are substituents. If the connection is to one of the end carbons, then technically speaking, you just change the name from butane to butyl, isobutane to isobutyl. That's all it is, if the connection is through the end carbons. However, if the connection happens in one of the middle carbons, so you have butane but connections in the middle, or isobutane and connection is through the middle, these things are going to be called differently. They're still going to call butyl, but they have a prefix in italics. They have the prefix sec and the prefix tert. And the reason why is because sec stands for secondary, meaning that the carbon in question has 2 other carbons bound to it already. And here the carbon in question has 1, 2, and 3 other carbons bound to it already, hence the name tertiary. So tert for tertiary meaning 3, sec for secondary meaning 2. And these are the new names that we will use as substituents. So you kind of have to be familiar with these shapes. Sometimes the terbutyl is drawn as a cross, so you'll see it drawn as a cross. And by the way, too, because these are single bonds, they don't need to be drawn like this all the time. The single bond on this end could be drawn pointing down. It's still a butyl chain attached through the middle, so it's still sec-butyl. So be aware of those tiny little changes. Okay, so second, third, italics. Oh, and one more thing. In terms of alphabetical order, second, third do not count. So you don't actually use him unless you happen to have sec-butyl and tert-butyl in the same structure, in which case you will use the prefixes tert and sec to distinguish which one comes first alphabetically. But in any other situation, second, third do not count. Okay, finally, the 3-carbon chain propane, if you treat it as a substituent and you attach from the end, you might have guessed it, propane becomes propyl. But isopropane is now going to become isopropyl, right? And the idea is that you're not really changing the structure of the alkane because propane is just propane, but the attachment is different. And so we're sort of like playing with this idea of butyl becoming isobutyl. Propyl becomes isopropyl if you attach through the middle as opposed to the end. Okay, so with all these types of substituents, I think we have a good ground um, to address most situations in terms of organic molecules that have substituents in them. So let's take a look at a few examples and let's try to figure out the numbering for them. All right, so here we have one molecule, and like before, it is important that you do give priority to functional groups, and the higher priority group has to have the lowest number. So that's something we're going to keep in mind, because when we look at this molecule, it looks mostly like an alkane. However, we do have that alkene present in there, so that's going to play a role, as you'll see in a second. The first thing I'm going to do is I have to go and find the carbon chain that from beginning to end covers the most carbons. And it is impossible to draw the organic molecule from beginning to end without having to lift your pen to go to draw something else and then come back to this. So here we're only allowed to go in sequence without breaking the sequence to count how many carbons we have. And one thing that you might see right here highlighted is that if you start at this point in the molecule, this end, and you go all the way to that opposite end, you will have the most carbons counted. So check this out. You have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Another thing too is that you kind of want to incorporate the carbons that contain the alkenes. So that's another little trick that you can use. But if you were to start, let's say, from this end, and I'm going to work my way all the way to the right, you will have 1, 2, 3, 4, 5, 6, 8, 9. That's less carbons that in the pink fragment that I highlighted. If we go now down, we'll have 1, 2, 3, 4, 5, 6, 7, 8, 9. Also less than what we have here. So this gives you the most number of carbons in a single chain, going from one end to the other in the entire chain without breaking the flow. Another aspect that we're going to talk about later on a different example is that you do want to give or you want to come up with a chain that has the most carbons present in it, but also the most substituents. And if you get to situations where you have a carbon chain that is longer but it has more substituents, you have to make a judgment call there, and we'll address one of those problems a little bit later. But before I get completely sidetracked here, let's start naming the substituents. So everything sticking out of this pink chain that has the most carbons present is a substituent. So everything here in black is a substituent. So let's start naming them. And this is the scheme once again, 10 carbons in the red scheme. Going the opposite way, in the blue scheme, we still have 10 carbons, but the numbers are changing. So let's name the substituents. The chlorine on this end is known as chloro. The carbon sticking out here is your methyl group. Up here, you have 2 carbons, which you might want to call initially an ethyl group, but that ethyl group is not bound to the parent chain. It's bound to an oxygen, which itself is bound to the parent chain. So this is your, it's technically an ether functionality, but we're going to name it just as ethoxy, as a regular substituent. Kind of like chloro, ethoxy is a substituent. Over here, notice what you have. You have 1, 2, 3, 4 carbons, and you're attaching through the middle. That is basically the setup for sec-butyl. And down here you have 3 carbons attaching through the middle. That's isopropyl. Down here you have 1, 2, 3, and 4 carbons. You're attaching through the middle. However, this is not a linear 4-carbon chain. This is actually isopropyl attached from the middle. So in reality, this is technically tert-butyl. And so what I would recommend when you're approaching these problems is find out first what's the longest chain. Once you know that, name all of the substituents sticking out of the main chain. And then you can proceed to name it. So we have 4 carbons, excuse me, we have 10 carbons in this molecule. So we have to use the prefix dec for it. Also, I'm going to start putting some numbers right here in association with these groups. All right. Now notice what I'm doing right here is I'm basically telling you the order based on the alphabetical sense, because we need to attach these things in the name of the molecule based on their alphabetical order. And third, as well as sec, the third and sec portions don't count. So technically it's the B that we count for alphabetical purposes. And that's why sec butyl and tributyl are marked as number 1 right now, because B is the highest in terms of alphabetical order compared to everything else. We have E, we have I, we have C, we have M, so C ends up being the next one. And I'm putting a 3 because we're about to determine which one, sec-butyl or tributyl, ends up being number 2. So chlor is 3 for C, right? After that, we have E, which follows alphabetically, so ethoxy is number 4. Isopropyl is number 5, and we end up with methyl because of the M. Now, in terms of sec-butyl and tert-butyl, as I mentioned earlier, they're both present in the molecule. So here, and only here, we're allowed to look at tert and sec to make the distinction. And S, alphabetically, comes before T. So sec-butyl will be number 1, tert-butyl will be the second one in the order. So notice what we have here. We have sec-butyl, followed by tert-butyl, followed by chloro, followed by ethoxy, followed by isopropyl, followed by methyl, and ending with desene. And the reason we're naming this desene is because we have 10 carbons and there is an alkene present in there. Okay, now in terms of the positions, notice that every time we have the number, hyphen, substituent. And then the numbers are always separated from the letters by hyphens, right? So the in-between numbers will have hyphen before it, hyphen after it. And as far as the numbers go, this is the red scheme, right? So chloro appears at position 2, which is what we have here. Ethoxy appears at position 4, sec-butyl at position 5, isopropyl at 6, tert-butyl at 7, and the alkene appears first at position 8. So we're putting the 8 in front of desene to let us know that that's where the alkene appears. If we follow the blue route, on the other hand, we now have desene appearing at position 2 because that's where the alkene appears first. Of course, everything gets rearranged because now methyl is at position 2, isopropyl is now position 5, ethoxy is at position 7, sec-butyl is at position 6, and tert-butyl is at position 4, right? So things have changed. Now, in order to determine which one of these two names is correct, you need to pay attention to the highest priority functional group, not substituent, but the functional group. And the functional group here is the alkene. So you want to make sure the alkene has the lowest value. So between 8 and 2, 2 is the proper number. So we select that as the proper name and the proper number scheme for this molecule. All right. As I mentioned earlier, you could have situations where it's not exactly clear where you're going to go for the parent chain, and here is a perfect example of that situation. And the number of substituents is what's going to give it away. All right, so if we look at this structure, there's a number of things we can do. Notice here that if we start right at the end of this green segment, we can go all the way here, but here we have a break. So we could go towards the blue segment, or we could continue going down into the black. And at the black right here, we have another break. We could go into the pink segment, or we could continue going down. But the other thing that you could also notice is that, well, okay, the green segment is worth 1, 2, 3 carbons until you hit this point. The blue segment is worth 1, 2, 3 carbons until you hit the same point. So there's really not much difference as to which you choose. And in such situation, you want to choose the chain that has the most substituents. So between the green and the blue one looks better because it's got that substituent present, whereas this one does not. So this might tell us, okay, we probably want to start from the blue one. If we keep going down, what we see here is that yes, we do have the pink highlighted, but technically going from the blue one to the pink will only give us 1, 2, 3, 4, 5, 6, 7, 8 carbons. And as you can see here, we have a lot more ground to cover, so we're going to continue going down. All right, so we're going to choose the one with the most substituents, so we stick with the blue one. And if we continue going down, now we have 1, 2, 3, 4, 5, 6, 7. Okay, here we have a little break as well. We could go all the way down or we could go all the way up. And notice here that we have 1 and 2 carbons, and if we go down, we have 1 and 2 carbons. So it's really not different in the sense that we're going to have the same number of carbons for the overall chain. But the red one happens to have more substituents than the pink one. So we're going to choose the red path as the proper path, meaning that everything that I highlighted in blue here is the actual parent chain. Everything else sticking out of it is nothing more than substituents. So looking at this, we have 1, 2, and 3 methyl groups. We also have an ethyl group sticking here, sticking out of the blue chain. We have a propyl group up here and an isopropyl group down there. And finally, we have 4 carbons attaching, in a linear fashion, and we're attaching from the middle. This is your sec-butyl group. So 1 sec-butyl. All right, now let's determine the number. From one end of the blue chain to the other, we have a total of 9 carbons. So the prefix is going to be non. And this is just a regular alkane, so this will be nonane. And alphabetically, we want to place sec-butyl first because sec doesn't count. B is what counts. So B comes before E comes before I comes before M, and M comes before P. So we have the following order, right? So sec-butyl first, ethyl, isopropyl, methyl, and then propyl. And now notice that because we have 3 methyls, we do have to use the prefix tri to emphasize the fact that we are dealing with 3 methyl groups. And we have the 3 numbers here separated by commas, 3, 8, 8, where the methyl groups are positioned. If we take the opposite route, the black route now, the numbering changes a little bit. We have the methyl groups at positions 2, 2, and 7. We have the sec-butyl at position 5 still, the isopropyl at position 4, and we have the ethyl group at positions 3. So that's how all of these numbers change. Here we don't have the functional group to tell us where we make the difference, where we determine which number gets the highest priority, lowest priority, etc. So what we need to do is count and compare them from top to bottom and see how many goods we get in terms of how many times do we decrease the number. And looking at the top scheme versus the bottom scheme, 5 and 5 is the same, so nothing there. 7 to 3, that's a decreasing number, so that's 1. 6 to 4 is a decreasing number, so that's 2. 3 to 2 is a decreasing number. 8 to 2 is a decreasing number, and 8 to 7 is a decreasing number. So we have 5 numbers that have gone down, so that's 5 goods. 4 goes up to 6, so that's no good. So we have 1 bad and we have 5 goods. The overall is 4 goods when we go from the red scheme to the blue scheme. Therefore, the blue scheme is the proper naming for the molecule. Okay, I hope this has helped you, go through the process of naming molecules and determining the numbering scheme for substituents. In the next lecture series, I'm going to tell you about how to name cyclic molecules.